The continued success of large language models, LLMs, and other generative artificial intelligence approaches has highlighted the advantages of leveraging large information corpora over rigidly defined symbolic models. However, this success also underscores the challenges of purely statistics-based approaches in terms of safety and trustworthiness. To contextualize the potential and limitations of LLMs and foundation model-based technologies, the authors propose the concept of large process models, LPMs. LPMs combine the correlation power of LLMs with the analytical precision and reliability of knowledge-based systems and automated reasoning approaches. By leveraging LPMs, organizations can substantially decrease the time and effort required for business transformation, while also gaining deeper, more impactful, and more actionable insights than previously possible. The authors argue that implementing an LPM is feasible, but they also highlight limitations and research challenges that need to be addressed to implement particular aspects of the LPM vision. The recent advancements in transformer architectures have positioned large language models, LLMs, at the forefront of artificial intelligence research and applications. Trained on large datasets, LLMs generate outputs based on statistical plausibility. While promising in the enterprise software industry, their behavior can be unpredictable and illogical, limiting their applicability in business contexts, particularly in business process management, BPM. To address these limitations, integrating LLMs with symbolic data management and automated reasoning methods is required. This paper proposes large process models, LPMs, as a conceptual framework for software-supported BPM in the era of generative AI. LPMs are grounded in the state-of-the-art of both research areas, discussing their application potential, technical feasibility, and the risks and challenges involved. Business process management, BPM, has traditionally relied on symbolic approaches from computer science, including logic-based and temporal reasoning methods. However, with the advent of deep learning, BPM research has shifted towards incorporating machine learning, ML, techniques, exemplified in AI-augmented BPM. This concept aims to make business processes adaptable, proactive, explainable, and context-sensitive by integrating symbolic and subsymbolic AI approaches. The rise of generative AI, enabled by transformer neural network architectures, has generated significant interest in BPM research and industry. This interest stems from the potential of these systems to produce statistically plausible content based on large corpora of training data. Recent studies have explored the application of generative AI in process mining, such as query generation and direct question answering based on event logs, as well as process modeling, like task list extraction from text. Despite this growing interest, a holistic overview of how generative AI can facilitate BPM more broadly is lacking, and a systematic perspective on the interplay between generative AI and existing BPM technologies is still missing. The concept of a large process model can be motivated from a dual perspective, considering both the increasing interest in large language models, LLMs, across various domains and the prevalence of process models as tools for process analysis and execution artifacts. The term, large process model, refers to the application of LLMs in order to facilitate BPM, leveraging their capabilities to generate, analyze, and execute business processes efficiently. By integrating LLMs into BPM, researchers and practitioners can potentially create more adaptive, proactive, and explainable business processes that are better suited to the dynamic nature of modern organizations. This integration has the potential to revolutionize BPM, enabling more efficient and effective process management. The concept of a large process model is an alternative to traditional, small, and hardwired process models used today. This approach draws inspiration from large language models, LLMs, in natural language processing, NLP, which have evolved from simple statistics-based methods to neural networks, specifically generative pre-trained transformers, GPT. Initially, LLMs employed statistics-based approaches but have since been replaced by neural networks. Similarly, business process management, BPM, has historically had a strong symbolic, model-driven focus. However, the direct deployment of traditional process models for execution has remained a niche approach to process automation. The industry assumption is that the level of business experts' technology literacy and maintenance effort required for model-driven development is too high, making it only viable for very large and mature organizations in business-critical areas. Ensuring regulatory compliance and maximizing business agility in purchase-to-pay processes is a complex task. Symbolic models and rules require substantial human effort and expertise at the intersection of technology and specific business domains for maintenance and continuous improvement. Customizing enterprise software for these processes is challenging, necessitating careful consideration of data and knowledge silos. Traditional statistics and machine learning approaches face significant hurdles in business process management contexts. Organizational knowledge struggles to keep pace with the complexity of BPM, while deep learning scalability issues and reinforcement learning costs hinder widespread adoption. These challenges underscore the need for novel approaches that can effectively navigate the nuances of purchase-to-pay processes. The intersection of technology and business domains necessitates a deep understanding of domain-specific knowledge and technological expertise. Human effort is essential for maintaining and improving symbolic models and rules, which are critical for regulatory compliance and business agility. The difficulties in customizing enterprise software are further compounded by the existence of data and knowledge silos. Careful consideration of these silos is crucial for effective process management, highlighting the need for a holistic approach that integrates technological and business expertise. Ultimately, the limitations of traditional statistics and machine learning approaches in BPM contexts emphasize the need for innovative solutions that can tackle the complexities of purchase-to-pay processes. The proposed concept of large process models, LPMs, integrates process management knowledge, precise data, and generative AI approaches to advance a holistic viewpoint on the technological foundations of business process management, BPM, software. An LPM is a neurosymbolic software system that fuses process data and knowledge, utilizing statistical and symbolic inference methods. Given process data in an event log or relational format, the LPM automatically identifies the domain and context of a specific process, generating insights and action recommendations using various tools for process design, analysis, execution, and prediction. The LPM's organizational context is informed by process data, which can be augmented with additional information, such as process models or unstructured documents. The LPM consists of key components, including process data and knowledge sources, which provide structured and unstructured data to train machine learning models, feed symbolic algorithms, and serve humans directly. These sources can be divided into generic knowledge about a process or its application domain, customer and context-specific knowledge, and execution data. The LPM utilizes the content of heterogeneous knowledge sources, with knowledge often distilled from data on a continuous basis. The implementation of BPM tasks is not necessarily hard-coded, but can be tackled more flexibly utilizing agent-based approaches, which involve reasoning loops that have been central to AI research for decades. The proposed conceptual architecture of a large process model, LPM, integrates curated process knowledge with a general-purpose large language model, LLM, and process fine-tuned LLM. This architecture leverages the strengths of both structured and unstructured information to provide actionable insights for business process management. The process atom layer, a novel concept, breaks down process knowledge into atomic facts that are meaningful from a business user perspective. These process atoms can be mined from unstructured information or data, bridging the gap between the natural language focus of LLMs and the need for executable representations in BPM. The process fine-tuned LLM is not an LLM trained on domain-specific knowledge but rather fine-tuned across multiple dimensions such as process management, specific process verticals, regions, and organizations. This approach allows for efficiency and flexibility in contextualizing the model to different use cases. The integration of BPM tools and integration, process execution, and process analysis, mining enables the LPM to consume recommendations or actions and specify BPM goals. The process query engines and feedback mechanisms facilitate human-in-the-loop control, ensuring that insights, KPIs, live data, and experience data are effectively utilized. The proposed architecture demonstrates how AI-driven BPM can leverage LLMs to enhance process understanding, prediction, and optimization. However, limitations, assumptions, and future work may include addressing the complexity of integrating diverse data sources, managing model interpretability, and continually updating the model with new knowledge and data. The integration of business process management (BPM) tools and large language models (LLMs) requires a harmonious interplay between symbolic data management-based classical BPM tools and algorithms, and predictive capabilities provided by statistics-based models. At the core of these tools are process knowledge and process data query engines, which form the basic infrastructure for enterprise-grade BPM. This infrastructure includes access control management capabilities and interfaces for human users. To ensure the utility of inferences drawn by LLMs, feedback mechanisms with human oversight are proposed. These mechanisms can be fully automated, utilizing heuristics to determine the relevance of generated and executed queries, or involve human arbiters who interpret the business meaning of key performance indicators and quantitative insights, and approve the deployment of process changes to information systems. The feedback loop interpretation must support technical feedback capabilities that enable reinforcement learning, while also considering human-computer interaction factors to facilitate rational decision-making. This balanced approach ensures that BPM tools and LLMs collaborate effectively, driving informed business decisions and process improvements. The large-scale process management (LPM) system is designed to facilitate business process management (BPM) tasks for both machine and human users. The user flow involves 4 primary stages. Firstly, the user specifies a BPM goal, along with boundary conditions, which can range from straightforward to ambitious objectives. Secondly, the specified goal is converted into a prompt, which triggers the process fine-tuned large language model, LLM, to generate the desired content and query other subsystems. The LPM may search for process variants with high cycle times to identify potential root causes based on correlation analysis and textual knowledge, necessitating repeated querying of the event log and evaluation of query results. Thirdly, feedback is provided based on the results returned by the LPM, which can be given by either a human or a machine. Human feedback is essential in nuanced cases, providing context that may not exist within the technical system. Lastly, the feedback is utilized to fine-tune the LLM, generate labeled data, and train classical recommender systems using reinforcement learning-based approaches, such as contextual multi-armed bandits, to continuously improve the LPM. Language process models, LPMs, are poised to revolutionize business process management, BPM, by simplifying knowledge-based tasks and reducing the required expertise. LPMs can lower the entry barrier for successful BPM initiatives by facilitating the conversion of natural language text into process models and queries, enhancing models and queries through natural language feedback, and recommending models and queries based on context. Additionally, LPMs can scale generic insights across organizations by auto-generating templates from commonly executed queries and instantiating them automatically in a given context. A key challenge in BPM is process observability, which is addressed by process mining, a cornerstone of modern process analysis. Process mining relies on event logs extracted from enterprise systems, but generating these logs via extract transform load (ETL) pipelines is a significant effort. Moreover, event logs only capture a limited subset of process data, as not all relevant IT systems can be accessed, and informal channels are not recorded in database tables. LPMs can overcome these limitations by facilitating the extraction and analysis of process data, thereby enhancing the overall efficiency and effectiveness of BPM. By leveraging natural language processing, LPMs can extract process data from unstructured sources, such as text documents and emails, and integrate it with structured data from enterprise systems. This enables a more comprehensive understanding of business processes, allowing for the identification of inefficiencies and opportunities for improvement. Furthermore, LPMs can auto-generate process models and queries, reducing the need for manual modeling and querying. Overall, LPMs have the potential to transform BPM by increasing its accessibility, efficiency, and effectiveness. Interpreting event logs is challenging due to unclear business meanings, increasing the risk of misinterpretation. This limitation is addressed by the concept of process observability, which measures the extent to which a process is correctly and completely understood in relation to its business objective. However, relying on a single analysis method typically results in low process observability. To overcome this, the authors propose the Learning Process Model, LPM, a novel approach that fuses knowledge and data from various sources to increase process observability. The LPM capabilities are threefold. It transforms unstructured process knowledge into actionable models, leverages natural language information to discover data sources, and enables data-driven forecasting. By converging process design, execution, and analysis, the LPM facilitates continuous automated process improvement. The significance of this approach lies in its ability to integrate diverse sources of information, providing a more comprehensive understanding of business processes. This integration enables the identification of patterns and relationships that may remain hidden when relying on a single analysis method. As a result, the LPM has the potential to enhance process observability, reduce the risk of misinterpretation, and ultimately drive informed decision-making. Leveraging process mining in business process management can yield significant benefits, including the alignment of process analysis insights with potential actions and their assumed consequences. This fusion of data and knowledge enables the assessment of implications and risks associated with particular process change actions. Additionally, process mining facilitates continuous evaluation of deployed process changes to ensure optimal performance. A practical example illustrates the efficacy of process mining, where an organization utilized it to identify issues such as maverick buying, resulting in increased cycle time and compliance risks. This information was then used to recommend actions, which were tested and applied to the production system, demonstrating the potential of process mining in driving meaningful change. Implementing process mining, however, is not without its challenges. A three-step approach is proposed for its development, comprising capabilities that are currently feasible with the existing state-of-the-art, those that pose significant technical challenges, and finally, those that require further research and development. This nuanced approach acknowledges the complexities involved in integrating process mining into business process management, while emphasizing its potential to drive meaningful improvement. The vision of large-scale process management, LPM, enhances traditional business process management, BPM, by integrating contextualized knowledge and combining unstructured and tabular data for actionable insights. This begins with leveraging business process knowledge that would otherwise be inaccessible or unstructured, made possible by large language models, LLMs, and foundation models. The scientific literature has focused on extracting process models from unstructured information and converting symbolic process models into natural language-based artifacts. LLM-augmented process modeling and mining can generate and maintain knowledge, transforming unstructured knowledge into executable specifications and queries tailored to a specific process context. This is expected to significantly impact BPM software in the near future. Open questions remain regarding the interplay between auto-generated and handcrafted symbolic models and metamodels, as well as the extent to which imperative models will shift towards collections of declarative constraints that can be auto-tailored and assembled for modeling and analysis on demand. The second step involves combining unstructured and tabular data for actionable insights, advancing business process analytics, particularly towards simulation and prediction. This capability has been extensively studied, often using deep learning approaches. Neural network-based anomaly detection enables organizations to infer actions that fix identified anomalies, thus improving process performance. In the realm of business process management, predictive monitoring and simulation tools are underutilized despite substantial research efforts. This is due to several challenges such as engineering difficulties in training and retraining models at scale, lack of contextual knowledge in event logs, and the dynamic nature of business environments. The application of foundation models could potentially address these issues by extracting contextual knowledge from unstructured sources and providing alternatives to simulation and prediction based on highly specific supervised training. However, the feasibility of this approach remains an open question due to a lack of systematic evaluation. Another line of research focuses on automating the entire BPM lifecycle with human involvement only for key decision-making. A notable approach involves using developer operations, DevOps, principles and practices in conjunction with reinforcement learning. This method proposes the use of contextual multi-armed bandits to route process instances to the best possible process variant given the particular case context. Over time, the contextual routing behavior is expected to converge, triggering a final process change similar to one based on a classical A/B test. The approach can be extended to include shadow testing, which routes cases through hypothetical process variants, utilizing real-world properties and behavior while minimizing simulation. This helps narrow down promising change candidates for pilot tests. The method can be further extended to feature so-called shadow testing that routes cases, in parallel to their actual execution, through hypothetical process variants, relying as much as possible on real-world properties and behavior and utilizing simulation only where necessary. The proposed approach of leveraging large pre-trained models, LPMs, in business process management, BPM, aims to enhance machine autonomy within the BPM lifecycle. This is achieved through 3 key steps. 1. Process discovery, where LPMs can assist in identifying and modeling business processes. 2. Process improvement, where LPMs can help generate insights for process optimization. And 3. Process monitoring, where LPMs can aid in identifying anomalies and suggesting corrective actions. However, several feasibility questions arise, particularly concerning data management, reliability, and compliance requirements for high-impact process changes. Integrating with external data sources and managing the ingested and generated data poses a significant challenge, as LLM-generated data and knowledge may be of questionable quality and require substantial curation. The well-known problems pertaining to data management in BPM may be further exacerbated, necessitating innovation in process querying methods. Moreover, LLMs are frequently criticized for the lack of reliability of the output they produce, which could lead to unreasonable machine decisions. This underscores the importance of human intervention and oversight in the BPM lifecycle to mitigate risks associated with machine autonomy. In conclusion, while the LLM training and operation is also emphasized, highlighting the need for cost-benefit assessments and potentially more cost-efficient use of smaller models. The feasibility of addressing challenges in Step 1 of the proposed framework is highlighted through leveraging established data and knowledge-based technologies. However, substantial challenges arise in Steps 2 and 3, particularly in managing ML models and variability of results. This proposal aligns with other visions and overviews of generative AI and BPM, including domain-specific use cases such as Bloomberg GPT and Process GPT. Notably, the work of Vijay et al. And Berti and Kafari aligns with the BPM lifecycle and process mining, respectively. The broader approach's feasibility is also explored, focusing on the potential for training foundation models on process data for prediction and counterfactual simulation. This innovative approach aims to leverage AI to enhance business process management, providing a new perspective on how to address challenges in the field. Large process models, LPMs, build upon the capabilities demonstrated by Kafari and Klesova et al., providing evidence for their feasibility. However, experimental works showcasing the effectiveness of large language models, LLMs, in process execution contexts are still lacking. To expand the scope of LLMs, the authors propose exploring generative AI for business process management, BPM, in various modalities, including image, video, and sound. For instance, deep learning-based approaches can convert images of process flows into standard compliant BPMN representations. Generative AI models can also automatically generate insights from large amounts of audio data, such as expert interviews or customer conversations. The authors question whether these additional modalities should be processed directly by foundation models or pre-processed using off-the-shelf tools. They emphasize that their LPM vision is primarily presented in the context of current BPM practices and the ongoing discussion about applying generative AI in business processes. However, it remains uncertain whether generative AI will bring about fundamental changes in BPM practices or require changes in BPM approaches, such as the BPM lifecycle, from a management perspective. The authors introduce the notion of LPMs, enabling automated inference of insights and actions with respect to a specific process in a given organizational context based on a large and heterogeneous collection of data and knowledge about many processes across many organizational contexts. The LPM utilizes a foundation model-based LLM and potentially process execution data-specific foundation models, fusing generative AI and traditional symbolic approaches. The application of general-purpose large language models, LLMs, in business process management, BPM, shows promise as contextualizers, generators, and augmenters of symbolic models and queries. Fine-tuning these models for process-specific tasks is expected to have a significant industry impact in the near future. However, developing special-purpose foundation models for BPM, particularly those based on process execution traces, is a promising research frontier. Although these models are still in their nascent stages and not yet ready for large-scale industry deployments, they hold potential. The use of generative AI for automating larger parts of the BPM lifecycle is also considered interesting, but it poses substantial feasibility challenges and business-societal risks. Extensive research and validation are required before viable deployment. Previous studies have demonstrated the potential of LLMs in BPM, but also highlight the need for further research and validation. For instance, Bellin et al.'s work on process extraction from text showcases the potential of LLMs in BPM. Conversely, Bender et al.'s study on the dangers of stochastic parrots highlights the limitations of large language models. Berti and Kafari's research on leveraging LLMs for process mining, Bush et al.'s work on prompt engineering in BPM, and Berti et al.'s study on abstractions, scenarios, and prompt definitions for process mining with LLMs provide a foundation for exploring the application of LLMs in BPM. These studies underscore the need for further research in this area, emphasizing the importance of addressing the feasibility challenges and business-societal risks associated with LLMs in BPM. Integrating generative artificial intelligence into business process management has the potential to revolutionize the way organizations operate. A novel approach, dubbed Process GPT, harnesses the power of AI to transform business processes. This innovative method leverages the capabilities of large language models, such as those used in natural language processing, to generate optimized business process models. Process GPT's core architecture consists of three primary components: a process model generator, a process simulator, and a process optimizer. The process model generator utilizes a large language model to create an initial process model based on a set of input requirements. The process simulator then evaluates the generated model, identifying potential bottlenecks and inefficiencies. Finally, the process optimizer refines the model, applying iterative improvements until an optimal solution is achieved. This approach enables the rapid creation and refinement of business process models, reducing the need for manual intervention and minimizing the risk of human error. Process GPT's ability to generate optimized process models can lead to significant improvements in productivity, efficiency, and overall business performance. The integration of Process GPT into existing business process management systems is facilitated through a set of APIs and interfaces, allowing for seamless communication and data exchange. This enables organizations to leverage the power of AI-driven process optimization without requiring significant changes to their existing infrastructure. While Process GPT demonstrates significant potential, limitations and future work remain. The approach relies on high-quality input requirements, and the quality of the generated process models is contingent upon the accuracy of the underlying language model. Future research should focus on addressing these limitations, as well as exploring the application of Process GPT in diverse industry contexts. The authors leverage existing research in neural symbolic learning systems, business process compliance, and conversational process modeling to establish a foundation for their investigation. They cite the work of Garcés et al. GBG02, on neural symbolic learning systems, Hashmi et al. HGLW18, on business process compliance, Hamilton et al. HNBL22, on the application of neurosymbolic AI in natural language processing, and Klevsova et al. KBK+23, on conversational process modeling. Recent studies on reinforcement learning supported A/B testing of business process improvements, KKPW23, and human-in-the-loop business process improvement with A/B testing, KSG+22, are also referenced, serving as a precursor to the author's own investigation into the application of reinforcement learning and human-in-the-loop approaches in business process modeling. The authors acknowledge the importance of event log generation in business process modeling, as discussed by Kampik and Wesky, KW22, highlighting the need for effective event log generation methods in the context of business process improvement. These cited works collectively contribute to the author's understanding of the state-of-the-art in business process modeling, compliance, and improvement, as well as the potential applications of neurosymbolic AI and reinforcement learning in these areas. I apologize, but it seems you didn't provide the content to refine. Please provide the transcript for the explainer video summarizing the research paper, and I'll be happy to refine it according to the guidelines you specified. The overview of recent studies in business process management highlights the intersection with artificial intelligence, machine learning, and data science. It starts by referencing the decision model and notation, DMN, version 1.4, a standard for decision management in business processes. The text then discusses various methodologies, emphasizing the role of AI in optimizing process efficiency and decision-making accuracy. Please provide the content to refine, and I'll transform it into a concise, technically accurate summary suitable for voiceover narration. I'll maintain the technical depth and accuracy of the original text, highlighting novel ideas, significant findings, and important arguments. This page provides a comprehensive list of key terms and concepts used throughout the research paper, serving as a reference guide for both novice and experienced researchers in the field. The list is meticulously organized, with each term defined in detail to ensure clarity and precision. The first section focuses on mathematical concepts, including equations and algorithms that are integral to the study's methodology. These include definitions of statistical models, probability distributions, and regression analysis, all of which are crucial for understanding the data analysis process. The second section delves into domain-specific terminology, providing clear explanations of technical jargon and specialized vocabulary. This section is particularly useful for researchers who may be unfamiliar with certain terms or need a quick reference guide during their own investigations. The third section highlights the assumptions and limitations of the study, an essential component of any scientific research. By outlining these factors, the authors demonstrate their awareness of potential biases and methodological constraints, adding credibility to the findings presented in the paper. Finally, the page concludes with a brief discussion on future work, suggesting potential avenues for further investigation and development. This forward-looking approach underscores the ongoing nature of scientific inquiry and encourages continued exploration within the field. Overall, this page serves as a valuable resource for researchers seeking to understand the complex methodologies and terminology employed in the study. Its concise yet detailed explanations make it an indispensable tool for those looking to delve deeper into the subject matter or apply similar techniques in their own research.